Hello students, welcome back. Let's go back to this discussion on discrete probability distribution. We discussed PMF last time and that wasn't too bad. And then we started talking about CDF. Now that was definitely more difficult. And of course in this video we're going to spend a bit more time on CDF. Let's take this example. The random variable y. And let's find out its cumulative distribution function, capital G of x, that is, the probability that this random variable y, capital Y, taking the real value less than or equal to x. Now, what are possible real values? Negative 1.5, 0.5, or 1. So, if this one here is less than negative 1.5, then that's impossible because none of these three will qualify. So always I begin from 0. Now what if this x value is greater than 1? Y is less than, say, 45. Then all these will be covered. So we have probability of entire sample space, so it's 1. So always, cumulative distribution function begins from 0 and increase to end at 1. Okay, here we go. There. And what is the PMF, probability mass function? That should be easy. We have negative 1.5, 0.5, or 1. And those are three possible outcomes. And otherwise, impossible. And those probabilities are 5/10, 3/10, 2/10 because those are the number of balls, and otherwise impossible, so probability 0. That's going to be easy, right? You can express the same thing in vertical tabular form or as a piecewise function form. They're all the same. Okay, all right. Now, how about the graph of the mass function? Alright, here's a probability mass function with this graph. Probability 5/10, 3/10, 2/10. Those are the heights. And the location of these dots are negative 1.5, 0.5, 1.0 respectively. Or equivalently, we can draw rectangles here with same width and non-overlapping. Which I prefer? I prefer dot plot expression than probability histogram format. I prefer this one. But this one is not wrong either. Now, the cumulative distribution function. So g of x is equal to probability of y taking the value less than or equal to x. Alright? And then when x is really small, so that, x is really small, say for example negative 100, then hey, none of this is less than negative 100, so I don't have anything, so probability is 0, that's not possible. Now if x is much bigger than 1, say 45, then less than 45 will cover everything, so probability goes up to 1. For example, if this one is say 0, in that case, it's going to come right in between here, right? So less than 0, so negative 1.5, yeah, it's covered. 0.5 is not covered. So only this is possible, so probability of red is included, the others are not. So we have this kind of situation. These three possible outcomes divide the number line in 4 pieces. Negative 1.5, 0.5, 1.0, those are possible. Less than that, impossible because from any x here, anything to the left, I don't have anything so far here to the left. So always I begin from probability 0. Now from here, come to the next interval here. Now anything here, x is supposed to be here, then if I go to the left from here, it'll cover one dot. So that's a possibility, and that has to be added. Remember, this is cumulative. That's a keyword. You have to keep adding. So add up that probability, and that's a cumulative probability up to here to all the way there. Even if I select my X here, everything to the left, it'll cover only one dot. But all of a sudden, when I cross this, and from here to there, I have now two dots. Red was there before, now I have to freshly add green, and that probability is 3/10. Remember, cumulative, that's a keyword. You have to keep adding up the probabilities. Now, in this interval, to the left, I have now 3 balls to consider. So keep adding and freshly add it 2/10. Again, the keyword is cumulative. Keep adding up the probabilities. So start from 0, add probability, add up another probability, add up another probability. All done. So we ended up with 1. So we ended up with this. 0, 5/10, 8/10, and 1 eventually. And then the threshold is these points. Negative 1.5, 0.5, 1.0. And as for the semi-inequality and inequality, that's really tricky point. And this one here is less than or equal to, not strictly less. That's the way it is defined. And then think carefully and think about why we end up with this expression, semi-inequality to the left and strict inequality to the right in the end. It turns out that fits, and that's not easy. It's tricky, but that's not easy, and I'll leave that thinking to you. Now, if you get really confused, then what did I tell you when we were in descriptive statistics all the way in chapter 1? When I had class interval, I gave you an example of grade distribution, right? Remember? And 90 to 100 is A, 80 to 90 is B, 70 to 80 is C, and so on. And what was my analogy? If you scored precisely 80, what's your grade? Is it C or B? It's B, right? 80 or higher, that should be on higher interval. Same thing takes place here. Negative 1.5 or higher, semi-inequality to the left, strictly inequality to the right, always. And why do we have that is actually related to this inequality here, which is semi-inequality, but that's a bit tricky. If you can follow all those and understand and prove it, that's great. If you can't, then still you have to remember the structure of those class intervals. And in my opinion, best way to memorize that structure is to associate it with your grade. If you scored precisely 70, then you belong to 70 or higher group and you earn C, not D. If you scored precisely 90, then you belong to 90 or higher group. You earned A, not B. Same thing goes here. So that's the way you can express the cumulative distribution function in tabular form like this, negative infinity to negative 1.5. Here, nothing is equal to infinity, so of course we have strict inequality. Otherwise, semi-inequality to the left, strict inequality to the right. Semi-inequality to the left, strictly inequality to the right, like this. And then you can express the same thing in vertical table like this. Same deal. And then the probabilities are, of course, coming as cumulative. Keep adding, adding, adding. Alright? Or you can express the same thing in piecewise defined function expression like this. Which I prefer personally. Personally, I prefer this piecewise defined expression, to tell the truth. Partly because it's difficult to typeset all those tabular format actually. But students usually tell me the tabular format is easier to understand. Okay, so that's how you get CDF. See? keep adding up, keep adding up, keep adding up. And finally, here's a graph. This time, I drew the graph of CDF and PMF together. So we have these dots, and then first, this jump is same as at the height of the red dot, and then this second jump is same as the height of this green dot, and the third jump is the height of this blue dot, because those probabilities are keeping added up. Or you can associate these probability histograms, and this jump is same as height of this rectangle. This jump corresponds to the height of this rectangle. Personally, I prefer dot plot. Do you have time for this? I don't know. I'll leave this final problem to each individual student. Instead, let me go ahead to this example problem. Find the CDF of the given probability mass function, and let's suppose that the mass function is given like this. So let's see, we have a probability mass 1/4, 1/4, 1/4, 1/8, 1/8, and 1/2. These are all possible probabilities and they add up to 1. Otherwise, this is wrong mass function. Okay, all possible outcomes must add up to 1, the probability of entire sample space. For example, if this had been blank, you should be able to fill it out because they have to add up to 1. And then, otherwise 0, it's nice to be here, but that's not really required because everybody knows. Okay, alright. And from here, find out the cumulative distribution function. Ready? Okay, here we go. Alright, these 4 numbers divide the number line into 5 pieces. X is less than 0.5. Of course, anything is greater than negative infinity, but this part is, not really required. Everything is greater than negative infinity, so even if you skip that, that's fine. I decided to put it. Next class interval, 0.5 to 1.25. Oh, by the way, these are to be changed again. And then the next class interval, 1.25 to 1.75, right? And then next class interval, next 1.75 to 2.0. And finally, greater than or equal to 2.0. And of course, less than infinity part is not really required, but I decided to write it anyway. And please note the structure of this inequality, the structure of this class intervals. Semi-inequality to the left and strictly inequality to the right. Always, no exception. Remember, if you scored precisely 80, then you belong to B, 80 to 90 group, not 80 or less group. Okay, alright. The first interval, less than 0.5, nothing was accumulated yet, so always you begin from 0. The last interval, everything was added in, so always you end up with 1. Okay, alright. From the first class interval to second class interval, as I cross the threshold of 0.5, what number was added? Keyword, cumulative. So what was accumulated here? What did I add? What number? Is that clear to everybody? Previously 0, but I added 1/4 because that's the probability mass. Next, this was the probability, cumulative probability, in the previous class interval. Now, as I cross this 1.25, something was added. What was it? Keep accumulating. All right, this is cumulative frequency, cumulative probability distribution. So it was up to here. And then I have to add something. What do I have to add at 1.75? Is that clear? And then from here, if I add 1/2, and if you do it right, you're going to get 1 anyway. And of course, you can simplify 0.0 plus 1.4, that's 1/4, right? And this one is going to be 3/8. And then this is going to be 3/8, 1/2, right? 3/8 plus another 1/8. So this is going to be 1/2 and then 1. Eventually, you're going to get that. All right? So that's the mass function. And then you can divide intervals like this. And then keep accumulating. With a color coding, it's a little bit easier to see. And simplify, no, actually not simplifying, it's the graph. The jump 1/4, 1/8, 1/8, 1/2, those are the jumps. They correspond to the heights. The second picture is not there. I wonder why. Okay, all right. The probability mass function and histogram put together in the same graph. So each jump corresponds to the height. Okay. And then, of course, if you simplify all these, you're going to get 1/4, 3/8, 1/2, 1, as we did before. So what did he do? Given PMF, we can calculate CDF. The same problem written in terms of piecewise defined function format. No difference there, and I'll leave the details to the students. As a matter of fact, this is generally true. Given PMF, you can always find out a CDF associated to it. So coming back to this, what do you mean by discrete probability distribution? It's either PMF or a CDF or both of them put together. Well, that's because if you know any one, you can determine the other one as well. We got half of that. Now, if you know PMF, then you can find out CDF through the same process of eliminating. What did I say? Eliminating? No, accumulating. Keep adding up the probability. It works all the time. It works in general. I didn't strictly prove all those symbolically, but the method that we went through, that applies. Okay, all right. We are kind of halfway through, or a little bit more than halfway through. We have to still do the other way around. If we know CDF, then how can we determine PMF? That's something we have to do, but that's something we're going to do in the next video. Stay tuned.